Hello AP Environmental students. Today's YouTube video is going to go over sag curves, which basically shows a graphical representation of what happens to a stream or a river when you have organic pollution dumped into that river, and it shows the effect on the dissolved oxygen and the BOD. So, as you can see from my diagram, right here we've got a stream or a river that has 5 distinct zones. We have the clean zone, the decomposition zone, a septic zone, recovery zone, and a clear zone. So again, if this is a stream or a river, I want you to imagine that your current is going towards the arrow. And we can say that this is the current. We can say it's the time after dumping. We can also say it's the distance from the actual dump site. So let's say our dumping is occurring right by the decomposition zone, and what's being dumped here is organic pollution. Organic pollution is pollution that came from or was once living. So this could be sewage spills that includes fecal matter from humans or other animals. It can be storm drains that have picked up debris on the way. It can also pick up things like dog feces or animal feces or goose droppings. Leaf litter, dead animals and plants from natural disasters like fires or mudslides, anything like that. Again, it has to be organic pollution, and again, organic means that it was once alive or came from a living thing. So our pollution is being dumped right over the decomposition zone, and what you'll see here with this red line is the BOD, or biological oxygen demand. And the biological oxygen demand is the oxygen needed by bacteria and other decomposers to break down organic matter. So you can see that in the clean zone, we've got a pretty low level of BOD, or a low level of biological oxygen demand. And then all of a sudden in the decomposition zone, we shoot straight up. We have this major increase because we have all of this organic pollution that's being dumped right here. So we've got this organic matter that needs to be decomposed. So all of a sudden, all of these decomposers need to do a lot more breaking down of organic matter, so they need a lot more oxygen. As we get further and further from the dump site, that biological oxygen demand decreases until we finally get it back down to normal levels in the clear zone. Alternatively, this also shows our level of dissolved oxygen. And our dissolved oxygen is the oxygen used by those decomposers to break down that organic pollution. So we start really high in the clean zone, and we have this sharp drop off in the decomposition zone until we finally get to this low point here in the septic zone. And this low point where I've got my star is called the sag point. This is why it's called a sag curve, because we show the sag of dissolved oxygen in a stream or a river or marine body of water. The sag point, again, denotes our lowest level of dissolved oxygen in our water. So we also equate that to the worst zone for marine life because our oxygen levels are so low. The marine life you'll find here is not going to be things like fishes and marine mammals and those kind of things because there is not enough oxygen for them. We're really only going to find bacteria and other decomposers like worms that are actually doing the decomposition of this organic pollution that's been dumped. Again, if we look at the zones on the opposite ends of the diagram, our clean zone, high in dissolved oxygen, it's going to be a really great area for fish and other marine life, so you're going to see a lot of your life in the clean zone. Also, after we have recovery after the pollution, when you get to your clear zone, again, you'll have your fish come back. You'll see a large increase in marine life because that DO level has risen again. One thing before we end this video, I want to talk a little bit about how this relates to cultural eutrophication. So what happens with our organic pollution is similar to what's going to happen with our marine life that ends up dying as a result of cultural eutrophication. So just a quick review. In this process, fertilizer runoff makes plant life grow rapidly. So we get these big algal blooms, these big increases in seaweed, and basically what happens is it blocks out the sunlight. When it blocks out the sunlight, our plants and marine animals that rely on those plants as producers die off. When they die, again, these are living things, so they're organic matter that falls to the bottom of the lake, and then decomposers need to come in and actually break them down. Just like in our sag curve, our decomposers need to use oxygen to break down that organic matter, and it depletes the DO that's in the actual lake. The problem with eutrophication in lakes is that it's a stationary body of water. So things aren't moving, it's not getting rid of that excuse me. It's not getting rid of that pollution. It's basically just sitting there. And because it's a stationary body of water, the DO is depleted throughout the entire thing, and marine life is never able to really come back. So this video again went over sag curve basics. It talked about the connection to eutrophication. And if you have any questions about this video, please feel free to ask me during class at some time this week. Otherwise, make sure you've taken good notes because you'll be using this in class. Have a great night.